Hello everyone. Today I, Dhruba Sarma, along with my project partner Vishal Hazarika, are going to present before you our BTech final year project, which is titled Vision-Based Underwater Docking Station Detection and Pose Estimation for Autonomous Underwater Vehicles. The project has been done under the supervision of Professor Kandava Kumar Sarma sir and Dr. Anjan Kumar Talukdar sir, also under the co-guidance of Dr. Surajit Deka sir. These are the outlines of our presentation. Now coming to the introduction. Autonomous underwater vehicles are some unmanned vehicles that operates independently without any constant human control. They are like underwater robots used for various purposes like deep sea exploration, oceanographic research, hydrographic surveys, and military applications, etc. Underwater docking is a crucial technology for enabling long-term operation and extending the capabilities of underwater vehicles. By enabling AUVs to dock with underwater stations, they can recharge their batteries, transfer collected data, and significantly extend their mission duration. Various challenges exist in underwater scenario like visibility, low visibility, turbidity of water. These factors provide significant impact in successful and smooth docking. So there were some drawbacks of traditional method. As in traditional method, a constant human control is very much necessary. But when the vision-based approach came into market, it becomes quite easier to detect any underwater object using deep learning-based models. Once the docking station is detected, then we go for pose estimation, which provides the AUV to successfully dock with the docking stations with the help of the three-dimensional guidance. So these are the some key factors that motivates us to do the project. Improvement of efficiency and safety of underwater docking operations, increment of the operational ranges of AUVs, minimization of reliance on human intervention, enabling support for innovative underwater applications. So these are the literature review. We have gone through almost 25 papers, but we have listed some of them here. So we have formulated two different problems as two different phases. So the phase one is the efficient underwater docking station detection with limited dataset using transformer-based object detection. And the second phase is pose estimation of docking station for proper and accurate docking of the autonomous underwater vehicles. Now the work done will be explained by my partner Vishal Hazarika.
Now let's discuss about the work done of our project. At first we discussed about the underwater docking station detection part. So this is the block diagram of the detection part. At first we have collected the data, that is data acquisition. After that we have performed data preprocessing, that is we have performed grayscaling and resizing of all the data in one size. And after resizing and grayscaling we have performed the data annotation and labeling in a website that is Overflow. After the annotation and labeling is performed, we have done data augmentation to increase the overall image from 400 images to around 2000 images. We have performed various data augmentation techniques like flipping, resizing, zooming, blurring, etc. After augmentation is performed, the resultant data set is used to train two different models, yellow version and RTDTR. Both the models are trained for 50 epochs, and after that, a comparative analysis between the matrices is performed. We have analyzed various matrices like accuracy, loss, precision, confusion matrix, etc. Apart from the comparative analysis, we have also performed the detection of the docking station using web camera. This is the annotation and labeling of our dataset using Overflow. This is the data augmentation we have performed like flipping, blurring, adding noise, etc. Now let's describe our dataset. Our dataset consists of 450 images which are annotated and labeled using Overflow. After that, we have performed preprocessing like resizing and grayscale. Then we have performed augmentation like rotation, flipping, noise, blur, etc. The augmented images are then split into three sets. The training set that consists of 1078 images, the validation set consists of 45 images, and the test set consists of 45 images. Now, for training of our model, we have used two of the state-of-art detection model, that is yellow version 8 and RTDTR. Now let's come to yellow version 8. Yellow version 8 is the most widely used detection algorithm that is currently the most popular algorithm available in the market. Now, let's study the structure of yellow. The yellow begins with a input layer where the image is given to the overall structure of yellow. After that, there is a backbone which is used for feature extraction from the images. From this feature extraction, the features are then fine-tuned by the neck part of the yellow structure. In the neck part, there is various processes like upscaling, downsampling, max pooling, which perform the overall fine-tuning of the extracted features. After that, the detection head give the final bounding box prediction result for the given image. The next model that we are using is detection transformer. Now, detection transformer is also a state-of-the-art object detection algorithm that leverages the power of transformer in the field of object detection. It is a future-proof technology. It beats most of the state-of-the-art technologies like yellow in terms of accuracy. Now, let's discuss the structure of RTDTR. So, at first there is an input layer where the images is input to the overall structure. Then there is a backbone which consists of a CNN layer that performs the feature extraction of the images. After that, the extracted feature maps are flattened and passed through a series of transformer encoder layers. And the output of this encoder is passed to the transformer decoder, which is responsible for generating prediction. After that, the output from the transformer decoder is processed through a detection head to predict the bounding box and class level. Now, the post estimation of the docking station will be discussed by my partner Dhruba.
Now coming to the second phase of our project, which is post estimation of the docking station. So pose estimation is nothing but a computer vision technique that figures out the position and orientation of a person or any object. Typically, it is done to observe the movement of a person's hand, elbows, knees, etc. But in our case, we have used it to locate the center of the circular docking station for smooth and perfect docking. Here comes the importance of pose estimation. Pose estimation is a very crucial part for AUV docking. There are a lot of benefits of accurate pose estimation because pose estimation provides the guidance to the AUV how should it move in accordance with the circular docking station. By having a proper pose estimation, the AUV can locate the center of the docking station and can move for alignment. Again, there are a lot of challenges in underwater scenario like turbid water, low visibility, reflection of light, and they may hinder the AUV to locate the center of the docking station. Now coming to the block diagram, once the docking station is detected, we go for pose estimation. So we feed the detected docking station with bounding box information to the pose estimation algorithm. The next step is basically a pre-processing part. The white LED markers make a closed loop, so it should be thresholded for detection of contour and to fit circle over them. Before calculating the distances, the camera calibration should be done to get some camera parameters such as focal length of the camera. This information is then fed to the algorithm to get x, y, and z axis distances. Now we will see whether the center of the docking station coincides with the center of the camera. If it happens, then we can conclude that AUV is perfectly aligned. Further, we can get an idea about the docking status. That means whether the AUV is allowed to dock or not. If the distance is equal to 25 centimeter, we can say that it is ready to dock. It is a conditional block that we have incorporated in our project. Now coming to the methodology, the first step is a camera calibration. Camera calibration is a crucial process in computer vision that determines some intrinsic and extrinsic parameters such as focal length, optical center, etc. So it is like how camera sees the world and translates the 3D object into 2D images. Uh, Checkerboard pattern is the most commonly used pattern for camera calibration. Uh, by doing the camera calibration, the focal length and optical center of the camera is determined. Now let's see how camera calibration is done with the help of the flowchart. A checkerboard with a known size is used to establish a reference for real-world coordinates. Each corner intersection on the checkerboard forms a 3D point in the real world with a specific XYZ coordinate. Then we capture images in various viewpoints and orientations. The number of images, if the number of images are more, the better would be the results. Then in OpenCV we use find chessboard corner function to identify the checkerboard pattern in the captured image. It detects the corners of the each square within the checkerboard and assigns them a pixel coordinate within the image frame. Then we use the function calibrate camera that leverages the 3D known coordinates from the step 1 and corresponding pixel coordinates from the step 3. So based on this information, the function estimates the intrinsic camera parameters. Now coming to the step 2, that is the implementation of the pose estimation algorithm. So the first step is thresholding and contour detection. Then once the docking station is thresholded, that means it is binarized for contour detection, and once the contour is detected, then a circle is fitted over the contours. Then we can calculate the z distance, that is the perpendicular distance from the center of the camera to the center of the docking station, and the z distance is calculated using the formula focal length into actual diameter divided by perceived diameter. Likewise, we can calculate the x and y distances also. Then we have incorporated the visualization and guidance. Then also we have incorporated some recommendation about the docking status in the algorithm. Now the results will be explained by my partner Vishal Hazarika.
Now coming to the results of our project. So at first we discuss about the result of the docking station detection part. So both the model are trained for 50 epochs. In yellow version 8 we got a class loss of 0.44. On the other hand in RTDTR we got a class loss of 0.35. Similarly we got a recall of 0.959 in yellow version 8 and a recall of 1 in RTDTR. We got the MAP50 value of 0.971 in yellow version 8 and a MAP50 of 0.978 on RTDTR. Also, we have seen the MAP50 to 95 values in yellow version 8 is 0.661, whereas in RTDTR it is 0.653. From the above results, we can see that RTDTR is performing better in class loss, recall, and MAP50. But in case of MAP50 to 95, yellow version 8 is performing slightly better compared to RTDTR. These are the confusion metrics for both the model, where in yellow version 8 we got 48 true positive and in RTDTR we got 46 true positive. These are the various graphs. These are the graphs based on the epoch versus precision. So we can see the graph. The graphs are increasing as the epochs are increasing. These are the epoch versus class loss graph. We can see that when the epochs are increasing, the class loss is gradually decreasing. We can see that in RTDTR, the class loss is decreasing even at a very small epoch. This proves that RTDTR is very efficient compared to yellow version 8 in many cases. These are the validation class loss graphs, and this is the overall bar graph that shows the mean average precision, class loss, and recall for both the models. This is the real-time prediction result for both the models. You can have a look. You can have a look. Both the models are performing really well in real-time situations. Now let's move to the 3D post estimation results. So after the calibration of the camera, we got a calculated focal length of 809.408 pixel. After the calculation of various intrinsic and extrinsic parameters, we then move to the 3D post estimation part. The first step is contour detection. So before contour detection, we first convert the image to binary value, that is black and white. After that, the contour is detected using various algorithm using OpenCV. After the contour is detected, we have drawn a circle over the contours using OpenCV. After the circle is drawn, we have done the 3D distance calculation, and we have found the x, y, z distances accordingly. The arrow in the figure 9 displays the alignment of the docking station and with respect to the AUV. When the two blue arrows meet together, we can say that the x and y distance will become 0. This is shown in figure 10. So in figure 10 we can see that the x and y distance are 0, and this means that the center of the AUV is perfectly aligned with the center of the docking station. We have considered a distance 0.25 meter at which the AUV will be ready to dock with the docking station. So you can see in the figure 11 that when the x distance and y distance are 0 and the z distance is 0.25, the display shows a command that is ready to dock, which give the explanation of our algorithm. So this is a quantitative analysis of the result that we have performed. We have calculated, we have measured three different distances in all the three axes, and we got different percentage errors, and you can have a look in the table. So now the conclusion will be given by my partner Dhruba.
Now coming to the conclusion, the real-time detection transformer model exceeds over the YOLO V8 in terms of recall and precision. We got a good accuracy in real-time detection of the docking station. Then we implemented the post-estimation algorithm. After implementing it, we achieved the guidance about the movement of AUV for perfect docking. We achieved the recommendation about the docking status. That means when the AUV reaches at the distance of 25 centimeters from the center of the docking station, we get a status like AUV is now ready to dock. We get an average error of 2% that can be observed in the distance measurement. So this is the bar chart or working timeline of our project. Now coming to the limitations and future direction. In future, we will be trying to integrate a hardware setup. We have to optimize the models to be useful for the better performance. We have to expand the training dataset in varied environments. For the time being, we have done the post estimation above water surface. Our future work will be focused on the underwater scenario. We have to optimize the post estimation algorithm for error reduction. Though the error is very less, we have to reduce it uh, for better performance. So these are the references that has been used in the presentation. Thank you.